Hút online hay sao ấy? Bây giờ ok hết rồi. Hình như hôm qua bọn chị chỉ dùng được một cái hay sao? Thế cho anh hello. Thế cho anh một cái. So good morning everybody. Welcome to the first day of our workshop. So I hope yesterday you all had a wonderful time with the conference dinner and after activity. So our first talk today is an invited talk given by the Dr. Siwa Yen from ASEAN. He's going to talk about the protostellar deformation in magnetite clouds is bipolar diffusion is the key. Right. So you have the 40 minutes for the talk and the question. I will announce you in the 5 minutes left.
Sure. Okay. Good morning, everyone. Happy to see everyone is still here, even after drinking last night. Yeah. So I'm happy to be here again, and thank you for the opportunity for me to share my research. So today I would like to talk about my recent work about disc formation and evolution at the early stage of star formation. So this has been discussed a lot in the past 2 days, so I believe I don't need to convince you that the B field is important, can affect star formation process, and we can study Magelan field with dust polarization. So today I would like to move on to a smaller scale, a few hundred AU around protostar, and to discuss whether like how Magelan field affect the disk formation and what's the key parameter determining the disk properties. So we know star and their surrounding disk form in magnetized molecular cloud. So we have this kind of dense core with Magelan field. Once it starts to collapse, and the Magelan field is dragged inward by inflow material from this kind of hourglass shape, which also presented in a previous talk. So once we have this kind of bent Magelan field, it will induce tension force. And that kind of tension force can slow down gas motion, the so-called Magelan braking. So in an extreme case, if the Magelan field are frozen in gas, and this process can be very efficient, so we will have a lot of Magelan flux dragging towards center, accumulating there, forming a very strong tension force, efficiently slow down inflow, remove angular momentum. In such case, simulation show that if the Magelan field are frozen in a gas, basically the ideal MHD gimmick, it can be so efficient that no disk can form. So now the question is, what's the mechanism to regulate this process so such that we can it can produce this kind of disk population as we observe in our universe. So here I show the result, the distribution of disk radius. These are all the disks have been observed in ARMA. For example, these are ARMA survey toward around region. They have resolved hundreds of disks. And we know typically the disk has a radii about a few tens of AU. So, the work we want to understand what's the mechanism determining the disk property, so we can have this kind of distribution. So one of the promising, probably the most natural explanation would be a non-ideal MHD effect, because we know molecular clouds are only weakly ionized. In such case, it cannot be in the ideal MHD gimmick. The gas Magelan field cannot be perfectly frozen in the gas. So here I show two simulation results. This one without efficient non-ideal MHD effect. So you can see basically the increasing Magelan flux around center disrupt basically everything, no disk form. And this the other simulation for comparison with efficient non-ideal MHD effect, and a nice disk form with a radius about 20 AU. So in our work, we try to discuss if we include a non-ideal MHD effect, can the model reproduce what we observe? So among the three well-known non-ideal MHD effects, Ohmic dissipation, ambiguous diffusion, or Hall effect, in protoscale envelope, which typically have a density around 10 to 6, and we know ambiguous diffusion will be the most dominant non-ideal MHD effect. So this plot shows diffusivity as a function of radius, density. So in this density regime of protoscale envelope, the ambiguous diffusion will be the most important one. So with the ambiguous diffusion, the B field is allowed to decouple from matter. So once the neutral material falling in, the B field can be left behind. So the importance of B field decrease as a function of radius. So this is also mentioned in US talk yesterday. So he showed in ISM or larger scale, larger than 0.01 parsec, these effects are not important. But on a small scale, like in protoscale envelope, this effect become more important. Okay, so now we try to see what's the prediction from this model. So here I quote the work done by Yuan Li, a series in Taiwan. Basically, she calculate what's the expected disk radius based on this scenario. Okay, so the idea is simple. The disk radius is basically determined by the angular momentum carried inward by inflow and in balance with those removed by mechanical braking. So if we write down this as an equation, it will be something like this. The first term is the angular momentum transport inward by inflow, and the second and third term is the mechanical braking. So if there's no mechanical braking, basically we can ignore these two terms. For example, if a B field line are not bent, then there is no strong tension force, then we will go back to the only with the first term, then that will be in the case of hydrodynamics. In hydrodynamics, the disk radius is very simple. It's coming by the amount of mass around center and what's the rotational energy of those material, and can written be like this. But with mechanical braking, the series, they can solve this, I cannot. So if we solve this equation, we'll get this. The disk radius is a function of diffusivity of amplitude diffusion, central scalar mass, and field strength. Yeah, so it looks very simple relation. And actually, as I mentioned before, the diffusivity is a function of a B field strength, density, and ionization. So these three parameters, eta, m, and b, are actually related. So if we assume a certain kind of chemical network, which determine the ionization fraction as a function of density, and these three parameters can be further simplified to only depend on the mass. So we can further simplify this into disk radius as a function of mass if amplitude diffusion is a dominant effect. And here I show the two solutions here. It's depending on the magnetic field orientation with respect to a disk rotational axis, where the B field is perpendicular or parallel to a disk. So now with this kind of prediction, which is very nice because it shows that the disk radius only depending on the mass, rotational energy, and magnetic field orientation. The three parameters we can observe, which means if the amplitude diffusion is a dominant process, given this model, we can predict what should be expected disk size distribution. So observationally, we can measure scalar mass. Here I show a JWST image of one of the young polar stars. If we zoom into a center, we can see this dark line, which discussed yesterday. And if we observe molecular line, we can see a gas motion is by ARMA. You can see one side is redshift, the other side is blueshift, showing a disk rotation. And from rotational velocity as a function of radius, then we can derive the scalar mass. And magnetic field orientation has been shown a lot in the past 2 days. Like with thermal gas polarized emission, we can know magnetic field orientation. If we can resolve a disk, we know the rotational axis of a disk, so we can know the relative orientation between magnetic field and rotational axis. If a disk is not resolved, we can use outflow, which usually along the disk normal axis. So use that as another indicator, so we can derive what's the angle between the magnetic field and rotational axis. So the final parameter we need is rotational energy. So here I show an optical image of a dense core. You can see a dark patch here. So basically that's where a dense core is. It's so dense, density high, obscure all the background light. If we observe molecular line, we can see the gas distribution and corresponding velocity field. So from this velocity field, we can estimate the rotational energy in a dense core. And this has been done by many people. And here I show the angular momentum distribution as a function of radius taken from different survey. So now we have everything we need. We know the scalar mass. Given a sample, we will have the scalar mass distribution. And from dust polarization, we can know magnetic field orientation. We also can get kind of probability distribution for magnetic field orientation. And then from the dense core survey, we can get rotational energy distribution. So combining the three, plugging in a model, which is straightforward, then we can predict what's the disk radius as a function of scalar mass. And these red contours shows the probability distribution of in this parameter space. Basically, given square mass, has the likelihood of disk radius. Okay, now we have everything ready. We just need to overlay with our observed disk radius, and this is what it is. So we compile a sample of 27 sources. These are all the sources with a resolved cavalier disk. And why is 27? I can only find that many in the literature. Yeah, but I believe with a future observation, we can have more data point. So these are all class 0 and class 1 young protostars with resolved disk, and they are all single, so there's no effect of deuteragonal interaction. And basically, this error bar due to our limitation to estimate the protoscale mass and disk radius. You can see our prediction will explain the observed disk radius of this sample. So we can convert this data point to a similar probability distribution. So gray contour show our observation, and red show our expectation from the model with a dominant amplitude diffusion. And you can see the two match pretty well. So now in our paper published last year, we demonstrate that with the model incorporating efficient amplitude diffusion, we indeed can explain the observed disk properties as a sample. So here's what model says. The sample arc disk radius is a function of scale mass. The blue and red shaded area shows the allowed solution in this model. So basically, the blue shows the solution from hydro, red shows solution from 9 g/d. So you can see for low mass protostar, maybe lower than around 0.3, they are in the regime of hydro. For those sources beyond that, they are in the regime of 9 g/d. So basically, our model suggests at early time or when the source, the mass is low, the disk radius basically regulate by hydro, determined by amount of rotational energy of a source it has. And after that, the system evolved. It has a faster rotation, fast inflow with twist and band B field, making breaking become important. And then the disk radius is regulated by a 9 g/d effect. Basically, it's determined by mechanical breaking, and the efficiency determined by amplitude diffusion. And with these two regimes, we can explain the observed disk population. So now we know as a sample as a whole, we can explain what we observe. Then could we see any feature directly due to amplitude diffusion? So that's our next questions. So if you look at simulation, here a simulation with efficient amplitude diffusion, it forms a nice disk. Because the B field now decoupled from the matter, which means the B field move at different velocity compared to a neutral material. And we know ions are coupled to a B field. So which suggests the ion and neutral are actually move at different velocity. So here I show the velocity profile as a function of radius extracted from this simulation. And this red solid line is the inflow velocity of a neutral material. And dashed line is the inflow velocity of an ionized material. So you can see there's a difference about 0.5 or so kilometer per second at the radii around 100 AU in this kind of simulation. So it suggests if amplitude diffusion is efficient, we may detect such velocity difference between neutral and ion. And the other feature is because now the B field are left behind, which means the gravitational energy increase faster than the magnetic energy. So if we compare mass to flux ratio, it's a function of radius. We'll see at outer part, the profile is more or less constant, where the B field is still well coupled to a matter. So this ratio does not change. At the inner radii, where amplitude diffusion is important, gravitational energy increase faster than magnetic field energy. So this number increase. So these are two features we are aiming for, whether there's we can find those to demonstrate this indeed amplitude diffusion. So to measure the mass to flux ratio and also to probe ion neutral drift, we select this target, which is a young protostar. It has a resolved disk with a radius about 20 AU. And we know if you look at this plot, radius, scale mass, the source is somewhere here. So it's possibly in a region of a dominant non-MCD. So what we need to do is to measure the mass to force ratio at a multiple scale, and also to compare the ion neutral motions in this source. So to measure the magnetic field strength or mass to force ratio, so we first use the JCMT Portal map. So we have seen a lot of this kind of map in the past 2 days. So I don't need to go to details. So basically with the DCF, we can estimate the field strength on this scale and then derive mass to force ratio. And the number we get is around 1 to 4. And as mentioned by Alex on the first day, depending on physical condition, we may use different formulation for DCF. So the reason why we have this figure 4 uncertainty is due to a different formulation. So we try to include all the uncertainty as much as possible. So on a small scale, if we're doing to a central 1 or 2 watt-second, here is a field structure traced by ALMA. You can see this kind of sort of hourglass morphology. And on this scale, DCF may not work because now the fluctuation is more dominated by a gas motion rather than a turbulence. So we do this in the other way, So we try to estimate field strength based on the dynamics. Basically, the gas motion we see should be a result from the force balance between the gravity and B field tension. So we can start with the MHD force equation, do some simplification. For example, we ignore magnetic pressure, we ignore thermal pressure, and we can end up with this equation. This part is kind of info and the gravity and tension. And if we can solve this, then we can estimate the field strength here. And this equation includes density profile, velocity profile, scale mass, field curvature, and these are all we can observe. So for example, we can have continuous image at different wavelengths obtained with ALMA. We can construct a model assuming density, temperature, and so on, go through radiation transfer calculation, convert to visibility, do a fitting. Here our observed image, our model image. We can compare the intensity profile as a function of radius. Black is from our observation, red is from our model. Through this procedure, we can estimate the density and temperature of our target. On top of that, we can add velocity profile, do the same thing, try to fit molecular line data. For example, here is the ALMA CA-KINO data. Through this fitting, we can try to explain what's the velocity feature, for example, shown by this precision velocity diagram, or the mean velocity as a function of radius, or line width as a function of radius. Basically, try to figure this feature to derive the info velocity. So now we have density profile, velocity profile, and magnetic field curvature. We can directly infer from our polarization result based on this hourglass shape. We can estimate the magnetic field curvature. And the good thing is this source is edge on. So which means all the colloidal components presumably will cancel out along the outside. So we can measure the curvature of a colloidal component. So now we have everything we need. Plug in this equation, we can get field strength, which is about 1 milligauss. And if we estimate the mass to force ratio, that's 10 to 30. Okay, so now we have magnetic field strength or mass to force ratio on 2 different scales. JCMT, several thousand AU, ALMA, few hundred AU. We can compare mass to force ratio as a function of radii. These two are our measurement on 2 different scales. Compared with the simulation result shown by these lines, we can see indeed in this source, we do see increasing mass to force ratio from outer to inner radii, which is a feature of efficient ambipole diffusion. So as I mentioned, if there's efficient ambipole diffusion, we may see different gas motion between ionized and neutral particles. So next step we did is we try to compare the gas motion traced by CA-KINO and H13CO+. So here I show the moment yield map showing a distribution of gas, and then mean velocity and line width. So you can see they have similar velocity pattern, but magnitude is different, especially in the line width map. The line width of an ionized molecule is much narrower compared to the neutral molecule. So if you zoom into a central part of a mean velocity map, you can see the pattern is indeed very similar, but the magnitude of a relative velocity is different. Okay, so because this source is h-on, so its line width is proportional to the inflow velocity shown by this cartoon diagram. So if you have an inflowing envelope, we look at h-on, its high velocity will appear as this line width in the spectrum. So we will have a broader line width. If we don't have this highly inflowing material, then we will lose this line width emission. We get narrow spectrum. So here I compare the line width of CA-KINO and H-CO plus as a function of radius. You can see at outer radii, the two are comparable, but inside maybe 100, 150 AU, the ionized molecule start to show narrower line width compared to a neutral molecule. So we can do the same exercise, build a model again, and for the ionized molecule, do a fitting, and then we can estimate the inflow velocity profile. And it's still ongoing work, but our current results suggest the inflow velocity measured with the H-CO plus line is about like 0.3, 0.4 kilometer per second, slower than that measured using CA-KINO. The radius is about 100 AU. So if you compare this number with that in the simulation, that here, 100 AU, while the difference is around 0.5 kilometer per second. And in this simulation, they form a 20 AU disk with efficient ambipole diffusion, similar to what we see here. And we also detect similar velocity difference between ionized and neutral molecules. So now, with this source or our work, we demonstrate that with a model considering efficient ambipole diffusion, we can explain the observed disk population. In one for source, which is likely in the region of a dominant non-ideal MHD effect, we also see the increasing mass to flux ratio from outer to inner radii. We may also detect the ion neutral drift. These are features of efficient ambipole diffusion. Okay, with this result, we probably can argue that ambipole diffusion is indeed acting in a perovskite source. And the next question is, what's the mechanism determining how efficient ambipole diffusion can be? So if you look at calculation, theoretically, diffusivity as a function of density, and this blue line is the diffusivity of ambipole diffusion. You can see given a density, there's about 2 orders of magnitude difference in diffusivity. And this difference due to the different ionization rate. If you have higher ionization rate, you have higher ionization fraction, then magnetic fields coupled with material better, then we'll have a lower value here. So there's a dependence on ionization rate. We can also look at the calculation, similar calculation, but comparing the result using a different grain size. For example, here they calculate diffusivity using a different Amax, and they get different profile. So these are two main parameters which may change the efficiency of ambipole diffusion. So our next step is try to see whether the source property can correlate with these two parameters. So ionization rate can be estimated from abundance ratio of some combination of molecules. These are based on the chemical modeling. For example, a ratio between DCO plus, HCO plus, and CO. From that, we can estimate the ionization fraction or ionization rate. So here are previous work toward NGC 1333. They show the ionization rate can change more than an order of magnitude across the cloud. So now we are having a JCMP program which have been allocated for more than 100 hours to observe this line, like CA-KINO, H-CO plus, DCO, toward a sample source where we know a disk property. And we try to estimate the ionization rate based on chemical network and try to compare what's the relation between ionization rate and disk radius. And this one is ongoing. Hopefully I can give you more update in the next second meeting. Yeah. And the other project I've been talking to now and Sean, whether we can estimate the disk property from polarization, because now with ARMA, we can have very nice polarization map, and we can have polarization flashing at different wavelengths. For example, here I show my previous paper, polarization flashing as a function of radius at 1.3 and 0.8 millimeter. So we can see a difference. So although the calculation shows that the Stokes eye may not be so sensitive to grain size, but polarization flashing does change. So here, this paper shows the polarization flashing at different wavelengths, 0.8, 1.3, based on different grain size. So I just learned this from this nice workshop. It's very handy tool, so we can calculate the polarization flashing as a function of frequency or wavelength. So in principle, we can use this tool, try to fit what we measured and to derive potential grain size distribution. And this can be compared again with the disk property, so we can know whether this property is determined by amplitude distribution, and which depends on the grain size properties. Okay. So this is my final slide. So summary our work. Basically, with our model calculation, we can explain the observed disk size distribution. In one of the source, we are indeed detect feature of amplitude diffusion, and we are now going for the larger sample to test this, whether we can see a similar trend in other sources. As the next step, we want to understand what determines the efficiency of amplitude diffusion, whether it's due to ionization rate or grain size distribution. So I will stop here and take questions. Yeah.
Okay, thank you. It's very nice talk.
Yeah.
I think now, because the effect of non-ideal MHD
Right.
is very
Yeah.
crucial for understanding the disk formation. So it seems that the cosmic ray ionization is one of
the important parameter.
And for me, I'm very interested in dust properties.
Yes.
So
Yeah.
the fact that if the dust grains are small, so the diffusivity is higher, so it can help to diffuse magnetic fields.
Yeah.
And in addition to using dust pi to model the dust population and then constrain the maximum size, I think we can also use the intensity, for example, at two wavelengths.
Right.
So we can derive the spectral index and,
Right.
and constrain the maximum size. And recently, together with Anael Mori and another person, so we propose a ALMA survey. So the survey named POPLIT.
Right.
So we try to map the dust emission from multiple scale from in Orion B. So hopefully the proposal would be approved.
Yes. Yeah.
So that we can use both polarization and dust emission to constrain dust properties.
Yes.
So that would help us to constrain whether dust properties or cosmic ray ionization are more important in determining this formation. But one particular comment here is in order to apply the current version of dust pi to the polarization, we need to make sure that the wavelengths here are optically thin.
Yes.
So I think for two wavelengths here, 1.3 and 0.87, it seems to be optically thin, right?
Yeah. So depending on which radius we are looking at, for example, if we are looking at this envelope outside the disk, in our data, we think it's optically thin. Yeah. So we get pretty high beta value.
Okay. Yeah. So I think it would be quite straightforward now because you already have the gas density from the previous slides. And if you know gas density, you know the dust temperature, you can plug in here and get polarization or different maximum size. So yeah, I think we should move forward with it.
Yeah.
Idea.
So move forward now.
Yeah, thank you.
Actually, I have a comment on that because Shiwei, he gave me the data for wavelength from ANMAP for me, and my responsibility to do this kind of thing and try to trade calculate the dust physics here. So yeah, we can discuss about that process later. Yeah.
Sorry, I maybe just one question and then.
Yes.
Okay.
Okay, great.
Yeah, just personally to comment from Tim and Ngọc that
Yeah.
we talked a little bit from yesterday
Yes,
that in
yeah.
the new version, one thing that we will have the optically thick effect.
Mm-hmm.
We have right now we assume that optically thick
Yeah.
for both intensity and polarized intensity.
Yeah.
But for the next version, we are updating right now for optically thick case
Yeah.
or general case. So where it's thin and where it's thick,
Okay.
it will
Yeah,
be
yeah.
thick. And I'm gonna just comment.
Yeah.
And we also can predict both SCD and also the polarized
Yeah.
spectrum and also extinction. But extinction in this case, I think we cannot use it.
Yeah, yeah.
But we have both to compare with the data and so
Yes, yeah.
the spectral index is very important here.
Yeah.
So my question is that again you tell us about the maximum of the radius of the disk can
Yeah.
be.
Yeah, yeah.
So can you show the slide again?
You mean our model prediction and this one or
Yeah.
yeah.
So that means all the observation here just within the boundary of the distribution.
Yeah. So let me clarify. First thing is basically what we did is we first find a sample with a resolved disk. So we measure a scalar mass, and that's one of the input to make a prediction. So given this scalar mass distribution, then we predict what the disk radii should be, and then we compare with what we observe here. So indeed, they are all falling in our prediction. Yeah.
That's very interesting because everything working with the magnetic field right now
Yeah.
is a plane on the sky.
Right.
And but the observation okay, also
All right.
show no effect of the another dimension of magnetic field.
Yes. So here, what we use, what we plug in is a probability of orientation.
Yeah.
So that probability is inferred from observational data. We only observe the behavior on the plane of sky. We need to infer what's the possible 3D orientation. So that's also plugged in here. So that's also one of the main reasons why there's the band for given scalar mass. So if it's more perpendicular, then you will go to a small, the other way around. If a rotational axis is aligned with the B field, then the value will be smaller. And if they are perpendicular, the value will become higher. So that's why we have a probability distribution.
Okay.
Yeah.
I understand that. Thank you.
Yeah.
Yes, and we have one online question from Jae-Hyun so that you can start, Jae-Hyun.
Hi, it's Yue speaking, and thanks very much for a nice talk. My question is, now in observation, you are using C18O and HCO plus, right?
Yes.
I wonder, how can we make sure they are sampling the same regions? Do they have the similar optical depths?
All right, so that's a very important point. We have to first make sure the two lines trace the same volume. So the first thing we did is to check opacity. So we make sure that both lines are optically same. And then what we did is we try different abundance profile in our modeling, where the result will change. And it turns out our estimated info velocity is not sensitive to the abundance profile we assume. So we assume, for example, constant abundance or step function or power law or this kind of profile derived from the chemical network. And we try all of this and found the derived info velocity are actually similar.
Okay, so is this a universal like conclusion like HCO plus and C18O that are tracing the similar region, or is that just for a particular
Yeah, I
region?
probably won't say it's a universal, but I think it's probably valid in a few hundred AU, but outside this, in the envelope a few hundred AU, outside this, probably that argument is valid, but beyond several thousand AU, I think the depletion rate is different, so now it's not valid. And also inside this, the density is too high, so ionization fraction can be very low. So in such case, ion neutral may not trace the same volume. So I think it's only valid within an envelope on a few hundred or up to 1,000 AU scale. Yeah.
Okay, thank you.
Yeah.
Is there any other question?
Okay.
Yeah, hi, Feng.
I have a question about the grain size and diffusivities. Wait, yeah, this plot. So you mean the smaller grains, if the grain size are smaller, you have a larger diffusivity?
I think that depending on which density regime. Yeah, you can see this profile is not linear and change a lot.
Okay.
Yeah. So in a high density regime, I think it's not a monotonic relation.
And why is that?
Why is that? Then next time we should invite to come over to come.
Oh, okay. Because from my understanding, the very small grains is the where the charge are
Yes,
deposited.
yeah.
So it's usually enhance the ideal effect.
Right. Yeah, that's right. Yeah. So for intermediate density regime, you are right. So small gas are well coupled to a gas and they are charged, so that can enhance.
Right.
Yeah.
So it is the case for the left part, but this part is
Yeah,
really
so I think for this part, it's getting more complicated because the surface area of a grain also change.
Okay, that's good to know. Thank you.
Okay, so I think one more parameter here is about the accurate estimates of magnetic field strength.
Yes.
So
yeah.
you are using the DCF methods to measure magnetic field strength
On larger scale, yeah.
a larger scale. So we all know that the DCF method has a huge uncertainty.
Yes. Yeah.
And it only provides a two-dimensional magnetic field. So if we know 3D magnetic fields, it will increase the magnetic field by a factor of something like a factor more than 50% or factor of 2.
Yeah. So I think the good thing about Hadron source is from DCF we can know the plane of sky basically toroidal field. And toroidal field is basically induced by rotation, and we know rotation should be smaller than the inflow. So we can know the upper limit of toroidal should be less than toroidal. So you can put like a square root of a 2 as the upper limit.
Okay, I think recently there is some detection of magnetic alignment of dust grains in the disc, right?
Mm-hmm.
So,
Oh, right, yeah.
So it could be used to estimate the magnetic fields.
Yeah.
In 3 dimension. I think that is the paper by the Ohashi something.
Yeah. Satoshi Ohashi.
But you have to choose carefully in which region, because if the region has a high density and then the alignment is not magnetic.
Right. I guess the issue is that kind of source is really rare to show B field alignment in a disk.
Right.
Yeah.
Okay. Yeah, thank you.
Yeah. So one caveat here is on core scale, probably DCF is still okay. Some people have run simulation, and we know there's some uncertain bifocal field. But on this scale, I have tried DCF, but it does not work. You give me a number that feels even stronger than gravity. So in this case, it's not valid. I guess because the field structure here is shaping by the inflow and rotation rather than the turbulence. So that's why we adopt different approach using a force balance, try to estimate B field strength on small scale. Yeah. So any more questions? Yes.
That's why the polarization vectors here are so much asymmetry. Yeah. What is the?
Yeah. So I think this also have been discussed by Qinfei, and they propose that that's due to toroidal field. So if you add toroidal field, they run some calculation. They think this side and this side will show the weaker polarizing intensity. But I think I'm looking in detail. But the argument is based on the twist of a field. Right. Yeah.
Yeah, okay. Thank you, Siwei, very much for a very nice talk and the discussion. So our next speaker is a PhD candidate, Nguyen Châu Giang from CASI. She's going to talk about the range alignment and disruption dynamic in low or intermediate mass class 0 or 1 young stellar object constrained by the dust emission polarization. So it's a 30-minute talk, Giang. You have 25 minutes for presentation and 5 minutes for question.
Okay. Ah, no, 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 no. I think it's okay. It's okay. I don't need the pointer. Okay. Wait a minute. So, good morning, everyone. So, my name is Nguyễn Châu Giang, a PhD candidate in the KC, Korea, and I'm working under the supervision of Professor Kim Hangs. So, today I'm going to talk about my research on constraining the grain alignments and description dynamics in the lows and intermediate mass glacial Young-style objects by dust emission polarizations. So, why I study about these subjects? So, we know that the star will form due to the gravitational collapse inside the dense mass of the molecular clouds. But during the collapse, so not only the gas density increased, but dust grains also had higher possibilities to collide and coagulate with another grains to form the larger ones. So we form the coevolution of the gas and dust in the star forming region. So the grain coagulation, they not only makes micron size grains to form the micron size, millimeters and kilometer size would be the seeds for the planet's formation. But dust grain will occur by the IMENSO due to the colder temperature inside the protostellar core. They also provide the surface for the complex organic molecules such as the methanol and ethanol to form. And on the hand, we know that dust grain can be aligned perpendicular with the magnetic fields, and they produce the polarized dust emission. With the polarization vectors perpendicular with the magnetic fields, and we know from lots of talks that dust polarization, they help us to trace the magnetic field morphologies and understand the dynamic importance of magnetic fields in regulating the star formation. And not only that, dust grain can also be charged by absorbing the electrons and ions. And the charged dust grains, they can control the magnetic resistivities, and this affects on how well the magnetic field will be dissipated inside the protostellar core to support the star formation. So even the wide effects of the dust grains in different aspects in the star formation, it's very important to understand in details the properties and the dynamic of dust grains in order to understand exactly how the planets and stars were formed. So as introduced previously, so dust polarization help us to study about the magnetic fields. But dust polarization, they not only tell us about the magnetic field morphologies, but it also be strongly controlled by the grains properties and how well dust grain can be coupled with the magnetic fields. So the observation toward glacial Young-style objects, they frequently report the very high polarization fractions of 5 to 30% in the protostellar envelope of 1000 AU scales, but just 1% of the polarization inside the protostellar is of 100 AU scales. So in order to understand the physics behind the big gap of the polarization fraction between the envelopes and the disk, so the Valdivia and 2019, so they performed the Okay, so I begin again. So the Valdivia, so they perform the synthetic dust polarization modeling using the radiative Tox alignment theories by using the radiative transfer course, and they change the maximum grain size from the 1 micrometer to 50 micrometers. And their results show that in order to reproduce the unmet dust polarization fractions, so very large grain beyond the 10 micron grains must be formed beyond the disk scales. But by assuming the maximum grain size of 50 microns inside the protostellar core scales, so the LOGOLEG in 20 and 23, they found that the rest itself, so the green, yellow lines, they cannot reproduce the grain alignment efficiencies referred by UNMAS, but the perfect alignment model can. So that means that in the protostellar core chaos, very last grains must have the perfect alignment with the magnetic fields. However, the problem is that inside the protostellar core gas, where the gas density can increase to 10 to 7 to 10 to 10 cubic centimeters, so the high gas and grain correlation, they can strongly randomize the grain alignments. So we expect last grain will be individually aligned with the magnetic fields and will produce very low polarization fractions, which is totally different with ANMA observation. So it's straight to the first question, that's what is the mechanism behind the perfect magnetic alignment of last grains in lower intermediate smart class 0 Young-style objects? So the presence of very last grain beyond the disk scales that not only found from the dust polarization fractions, but it also revealed via the low dust opacity index beta around 1 when we observe 500 AUs of the Young-style objects. So one scenario that can explain the presence of very last grains inside the inner envelopes is due to the Asfundos model proposed by Tsukamoto in 2021. So basically, very last grain, they conform inside the protostellar disk, and they can be uplifted by the gas drag force, and then they enter the outflow space, and then they transport into the inner envelopes via the outflows. And recently, by analyzing the Callisto protostellar core sample by Murray in 2020, so Capisuto in 2023, they found the clear correlation between the low dust opacity index around 1 found in the inner envelopes and the high outflow mass loss rate. So that's my support for the Asfundos motion. However, when dust grain they migrate inside the protostellar outflows, they can be rotationally disrupted by the mechanism named RADDIS, introduced by Huang in 2019, because the protostellar outflows have very low gas density and very strong radiation fields. So it's raised the second question, that whether RAS the effects into the Asfundos model. And second, if the RASD is activated, so how it constrains the grain properties around the protostar. So for the first question, the key points is we must understand in details how dust grain can be aligned with the magnetic field inside the protostellar core chaos. So back to the theory of grain alignments. So we know from the many previous talks that basically, dust grain can have the external alignment with the magnetic fields by the RAS or MRAS theory. And the difference between the RAS and MRAS is that for RAS, so only just 25% of grain can be aligned with the magnetic field at high chase. But for the MRAS mechanisms, so with the half of the iron inclusion, so dust grain can have the perfect alignment with the magnetic field, regardless of their properties and their orientation in space. So, and secondly, the study of Huang in 2022, he found that the inelastic realization, they can help micron and very last grain to have the fast internal realization inside the protostellar core scales. So we suppose that my MRAS and inelastic realization will be the mechanism behind the perfect alignment of very last grain inside the protostellar core. So in order to test our theories, so we improve the Polaris radiative transfer course. So basically, we perform the detailed modeling of the internal and external alignment of dust grains, depends on the grain's magnetic properties. And then we use the Polaris to model the grain alignments. And then we use the grain alignment test in order to solve the polarization for stock parameters. And the result will be compared with ANMA observation in order to test our theories and try to constrain the grain properties. So to be more details, so we adopt the embedded simulations of the intermediate smart class 0 Young-style object from Le Goulet in 2023. So we consider the central luminosity of 100 solar luminosity, and we consider one model of paramagnetic grains and 4 models of superparamagnetic grains. We also consider the different values for the inelasticity and then perform the synthetic modeling at 1.3 millimeters. So before we compare with ANMA, so we try to simulate the ANMA observations by using the SimObserve and SimAnalyze stars in the CASA. So we observe with the 3 ANMA configurations, C2, C4, and C6, and perform the observation for 3 hours per each configurations. So we observed 2000 AU scales, and with the synthetic PSI 140 AU. So I show here, this is the example of how the dust polarization degree map looks like before and after we filtering with the CASA. So basically, after filtering with the CASA, we can recover 1000 AU of protostellar core scales. So the polarization fractions in the outer region is higher compared with the synthetic data because of the leakage of the stock eye emission. But in general, we can recover rather well the polarization degree distributions. So that means that the filtering effects do not significantly affect into the intrinsic polarizations emitted from the young-style objects. And we can use these results in order to extract again the test properties and what happened inside the young-style objects. So first, in order to understand the mechanisms that's driving the perfect alignment of the grain in young-style objects, so we consider the model of superparametric grains with 5 iron atoms per cluster and assume the Amax of 50 micrometer. So with this configuration, the grain will be aligned with the magnetic field by rad only. So in this figure, we show the mean variation of the polarization fraction and the normalized gas column density from the envelope into the disk scales. So the black line shows the mean value of the 10 young-style objects observed by the ANMA. The brown one shows the results for the perfect alignment models. The orange one shows the results of the Polaris, but we don't consider the effect of inelastic relaxation. And the last one is the result when we consider the effect of inelastic relaxations. So we can see that when we consider the effect of inelastic relaxation, so more micron size can have the fast internal relaxation, and it has to increase the next polarization degree. But in general, we see that with rad only, we basically cannot reproduce the unmatched observation polarization fraction. So that means that rad itself, they cannot explain the unmatched results. So then we increase the number of iron atoms inside each cluster from 5 to the 10 to 3. And in this configuration, the grain will be aligned with the magnetic field by embrace mechanisms. And because of the embrace, so grain can almost have perfect alignment with the magnetic fields. So it generally increase the next polarization fraction from around 5 in the envelopes to the 10s is rather much well with the unbiased observation range in the envelope. But when we move into the inner envelopes of this range, so the embrace and planet realization itself, they cannot reproduce the unbound observation because micron-sized grains still have the slow internal realizations. And in this case, with the help of inelastic realization, so micron-sized grains and very large grains, they can have the fast internal realization, and it has to increase the next alignment decrease. And as a result, with our result, what I mean is the red ones, it can reproduce rather well the polarization degree grains observed by ANMA from the envelopes into the disk scales. So we suggest that the embrace mechanisms and inelastic realizations and superplanet realization. This is the mechanism behind the perfect alignment of very last grain in young-style objects. And then in order to understand what is the configuration of iron inclusion, that's the part for the ANMA observation. So in the left side, we change the number of iron atom inside each cluster. And we found that in order to reproduce the ANMA observation, so those grains must be superparamagnetic with at least 100 iron atoms per the cluster. And then next we also changing the maximum grain size to see that when we take into account the effect of internal and external alignments. So what happenings? So we see that in generally, the polarization fraction will increase with the Amax because of the extensions of the alignment side range. And we found that in order to explain the ANMA observation, so the grain must grow to beyond 5 micrometer inside the inner envelopes and 15 micrometer inside the disk. And the second point is that we see that with the old model of the grain's magnetic properties and maximum grain size, so the polarization fraction always reduced toward the inner region. So we suppose that the reduced internal alignments and embrace mechanism will be the reason behind the depolarization effects also within the 1000 AU of young-style objects. And lastly, we try to change the stellar luminosity in order to understand the effect of luminosity on the dust polarization. So we found that if the 50 micron grains, they can distribute over 100 AU of protostellar corpuscles. So the stellar luminosity, so basically they're not affecting to the animal observation. So that means even star only have the low luminosity, we still can reproduce the perfect alignment of the grains. But we found that in case that only 10 micron grains and smaller distribute over 1,000 AU scales. So when we reduce in the lower luminous protostars, so we have the lower polarization functions because of the significant reduction of the alignment side range by the RAS mechanisms. So for the first questions, so we conclude that the protostellar grains must be superparamagnetic material, and they can have the efficient alignment with the magnetic fields in the protostellar corpuscles by the chance effect of the MRAS mechanisms, inelastic realizations, and the supermagnetic realization. And we also suggest that the reduction of the internal and external alignments by increasing the gaseous dampings is the reason causing the reduction of the polarization fractions with the gas column density within the 1000 AU scales. Then for the second question. So in order to do that, we adopt the same embedded simulation as we studied for the previous study. So from the gas density profiles and the gas velocity profiles, so basically we calculate the gas velocities based on the balance between the drag force and the gravitational force. And we assume that grain will move constantly across the outflows with times. And secondly, from the radiation field strength that we got after perform the Monte Carlo radiative transfer with the Polaris, so we can determine the RAS. And then we can calculate the evolution of the grain angular velocity by the RAS while grain is transporting inside the outflows. And then we compare the angular velocity of those grain with the disruption angular velocity in order to determine what size of grain will be destroyed by radiation. So for the model setup, we first consider the extreme case that the stellar luminosity of 100 stellar luminosities. We consider the three different models of the grains. So the first case, highly porous grains with the tensile strength 10 to 3 to 10 to 4. The second is irregular high grains, is more complex, so it has a higher tensile strength from 10 to 5 to 10 to 6. And last one is considered two models of composite grains, which have the tensile strengths of 10 to 7 to 10 to 9. And all the results here is from the laboratories and the numerical modelings of tensile strength of the grains from inside the protostellar disk. Okay, so I consider first the result for the highly porous grains. So I show here, this is to understand how the disruption side they will evolve with times when the grain is transported inside the outflows. So the upper row, they show the maps of the minimum disruption size. This is the scale of 500 and 800 AU below the protostar. So in this area, basically the outflows and the surrounding, this is the outflow cavity world. So this one shows the minimum disruption size with the color bias from 0.5 microns to the 20 microns, and the lower row shows the distribution of the maximum disruption size with the color bias from the 20 microns to 500 microns. So we found that if when the RASD is activated for 1 year, so the grain beyond the 1 micrometer, they will be quickly destroyed by the RASD within the 300 AU scale of the outflows because of the low disruption thresholds. And the disruption size will last from the 1 microns up to 50 microns in the lower rows. Then we show the results if RASD activated for 5 years. So after the 5 years, small grain which is survived by the RASD, they will transport outwards, and thus causing the expansion of the active region of the RASD. And on the other hand, so large grains in the high Z's at the beginnings, they also have the larger times in order to reach the disruption thresholds and be destroyed by RASD. That's further help to the expansion of the active region of RAS from the 400 AU inside the outflows up to the 800 AU of the outflows after 5 years. And then with the if RAS is open, it activate more up to the 100 years. So we found that after 100 years, almost the outflows will be dominated by the submicron grains beyond 0.5 micrometers, and only the small amount of submillimeter grains beyond 300 micrometers can be survived by RAD. Then we consider the extreme case that rest can be activated with, for the 100 years. And here we do understand how the dust population will distribute inside the chest and outflows. So in this figure, I show the distribution of the minimum dispersion size as the functions of the gas velocities and the gas column densities. So the blue spot is for the properties inside the outflow cavities, and this green box is for the properties inside the chest. The upper rows is for the minimum dispersion size, and this one is for the maximum dispersion size. So we found that if rest can be operated up to the 100 years, so almost the outflows will be dominated by grains smaller than 0.5 micrometers. Then we try to test for the K of irregular grains and composite grains. So we can clearly see that if we increasing the compactness structure of the dust grains, so dust grain could be hardly aligned, destroyed by the rusty, and consequently the dispersion size will be reduced. So for example, if grains are composite structure, so only a part of grains inside the outflow will be destroyed by rusty, and the outflow will be we have the presence of micron-sized grains below 3 micrometers and very large grain beyond the 50 micrometer. And since we found that they have the high impact into the transportation of dust grain inside the outflows, so it turns to the next question, that whether the rusty affect into the dust polarizations. So in order to do that, we implement the rusty into the Polaris course, and we assume that grain to be addressed inside the Polaris. So we do some tests in order to verify the verification of rust in the Polaris, and we found that the result of rust Polaris can reproduce rather well the description size distribution for irregular grains and the composite grains. So we can use the Polaris results in order to predict how rust affecting to the dust polarization. So you indicate that with our rusty, we expect to see the excess of the polarization degree along the outflow cavity wall and in the envelopes, because very large grain will present here and can have efficient alignment with the magnetic fields, and it have lower along the outflow cavities because of the presence of helical field due to the launchings of the outflows. But when we consider the rusty into account, so if grain have the composite of the irregular structure, so the polarization degree distribution do not change. And the reason is because composites and irregular grains, they only destroyed by rust inside the outflow cavities. But the outflow cavity have very low gas density compared with the envelopes. So the contribution of dust emission, dust polarized emission from the outflows is subdominant to the contribution of dust emission in the envelopes. So that's why we do not see the imprint of rust in this case. But in contrast, if grain have the highly porous structure, so dust grain not only destroyed by rust inside the outflow cavities, but along the outflow cavity wall and also in the envelopes. So rust was so strong enough in order to destroy very large grain we have the porous structure. And as a result, we see the polarization fractions along the outflow cavity wall, they reduce from the 30% to around 10% because of the effect of rust. However, when we compare with the effect with the result from the dynamic approach, so we found that this figure, they only happens if the intermediate mass protostar, they can maintain the 100 solar luminosity for over 20 years. So if the protostar produce lower luminosity than these values, or they produce the 100 solar luminosity, but they only activate shorter than 20 years. So basically the dust polarization picture does not change. And so the last one is we need to understand the condition for rusty to be activated inside the intermediate mass protostar. So here we show the results of the distribution of the minimums and description size as the function of gas velocity and the gas column densities, in case that the central luminosity is 5 solar luminosity and 20 solar luminosity, and consider the case that rusty operates for 1 year and for 20 years. So we found that for highly porous grains, so even the central luminosity produce the 5 solar luminosity, so rust is strong enough in order to destroy the micron-sized grains inside the outflow base short after the 1 year. And if the luminosity is higher, so they will affect the grain much faster and stronger. So we conclude that rusty, they can start to destroy the porous grains. We have the low maximum tensile strength within the 1 year. if the intermediate mass protostat produce the central luminosity greater than the 5 solar luminosities. So for the second question, so our finding is we suppose that rats can destroy porous grains of size larger than 1 to 3 micrometers inside the outflow space. Just within 1 year, if intermediate mass protostat produce the luminosity greater than 5 solar luminosity, and such descriptions is will they temporarily prevent very large grains and sub-millimeter grains from transporting from the disk into the inner envelopes. And it will let the high abundance of submicron grains in hand velocity to be the dominant polarization, less polarization inside the few hundred AUs of the outflows. And this action will stop until the intermediate mass protostat they reduce the luminosity to below 5 solar luminosities. And secondly, we find that the RASTI, they can reduce the polarization fractions along the outflow cavity wall and the inner envelopes by a factor of 3. If grains have the porous structure and protostat, they emit 100 solar luminosity for over 20 years. So this is the result for the intermediate mass, but we expect that in the case of the high mass protostat, that's produce higher luminosity up to 10 to 3 or 10 to 4. So maybe RASTI will be affect more on the dust properties and also the transportation of dust grain from the disk to the envelopes in the case of the high mass. And as we know, the dust grain will affect a lot into also the magnetic resistivities. So it also can affect into like the effects of like the ambipolar fusion and how this effect they have to the disk formation. And for the last couple minutes, so okay, the last couple minutes. So actually we found that in order to reproduce the animal observation, so we need very large grains. But our model is under assumption that grain have the aspect ratio of 2. That means large grain have the elongated structure. And also from the previous talk of Chomsky, so he found that inside the Starless core, so those grain not only must grow to micron size grains, but the grain SEO ratio must also larger than 1 in order to reproduce the observation. So it's right to the question that's why large grain they have the high aspect ratio, because usually we expect that when grain grows, they will become more spherical. But if grain become more spherical, so they will be less alive and less produce polarized dust emission, and basically we cannot reproduce animal observation. So this is just so one scenario is that grains grows anisotropically. So if, for example, grains are aligned with the magnetic fields and they drift things perpendicular with the magnetic field by, for example, the ambipolar diffusion, so they will receive the more grain in this direction than in this direction, and it may have grain to become the oblet shape. So it's just the preliminary results. So we try to models that we include the grain size from 0.5 micron to 0.25 microns, and they assume that such grains are randomly moving due to the turbulence, but we consider 0.1 micron grain to be drift along one directions with the different velocities. And then we try to models about the grain coagulation effects in order to understand how the mass distribution and how grain grows. And secondly, we try to calculate the increased rate of the AX and the AZ direction. So this is the results. So this is the variation of the AY. This is the direction perpendicular parallel to the magnetic fields, and AZ, this is the direction along the drift direction. So we see that after the time flies, so the AZ, this means in this direction, they increase faster compared with the increase of the size in this direction. And this is our just expectation that, for example, for 0.05 micron grains, so they just grow isotropically, so the aspect ratio is 1. But for grain larger than 0.1, so they grow anisotropically, and the SEO ratio they can increase from 1 to around 1.17 after the 50 kiloyears. And if the drift velocity is higher, so we expect the aspect to error will be increase more faster. For example, 0.1 micron grains, they can increase the aspect ratio from 1 to about 2.4. And this is just the preliminary results. So in the future, we tend to perform the n-body simulation to understand that's whether our theoretical approach, they can match with the n-body simulations. And if it is success, so we hope that we can incorporate this into, for example, the MAD simulation, so that now we not only can model how the gas involved with times, but also the grain size and also the grains aspect ratio change with times. And have the accurate model about the gas and the dust distributions is very important for us to understand exactly what happened inside the cores and to better interpret our observation. And this is the end of my presentation. So thank you a lot for listening.
Any question from audience?
Thank you for the very nice talk. Well, a lot of work done. So can you go back to the next?
Yeah, can you? I cannot hear.
Oh, sorry. So can you go to the drifting case?
Yeah.
Maybe I can start from the most recent one.
Yeah.
So I have two questions for this one. First, why is grain drifting perpendicular to the B field?
Yes. So usually in the, for example, grain can drift across the magnetic fields by the ampipolar diffusion. So basically, this is the magnetic field direction. So grain can move along the magnetic fields. But in the case that grains, it have the charge and the neutral. So the neutral grain, they just don't feel the magnetic field, so they can just come across in the perpendicular direction with the magnetic fields.
Okay.
Yeah, so what I mean is ampipolar diffusions, they can explain why grain can be perpendicular with the magnetic field direction.
Yeah.
This is one case.
In case of ampipolar diffusion, I can understand B field is drifting in one direction, but it does not prevent grains to be moving along B field.
So this is, for example, this is the cross scales and this is the magnetic field direction. So grains, they're easier to move along this direction, but if they only move along this direction, so they will produce very fast, very this like this, but and it's kind of collapse. So the one mechanism that grain in this direction also can move inwards is that the ampipolar diffusion, because if grains is charged, so they will feel the magnetic field and keep in this, but for neutral gas, they don't feel the magnetic field, so they can move in this direction or even in across the magnetic fields. Yeah, so this is one scenario. That's how wide grain can move across the magnetic field direction.
So the second question is, what do you expect during this kind of different coagulation on the porosity? What's the impact of this different coagulation scheme on the porosity of dust grains?
On the porosity?
Right.
I think in the case that grain are addressed and the coagulation in isotropics, so I think they will become a higher porosities. But in case that grain is drifting along this direction, so you understand that they will collize and take the more grain in this direction. So maybe because they move fast, so they may make the grain become more touched into together, and it make the porosity may be higher compared with the case of isotropics. So this is our guess, but we need the simulation to see whether it works or not.
The other question is
Yeah.
the aspect ratio
Yes.
connected with the first work. So to my understanding, the polarization fraction, the absolute value of that is degenerate between the aspect ratio of
Yeah.
dust grains and the degree of alignment. How are you able to break the degeneracy?
So actually, we agree that if the grain the growing, but the aspect ratio is decreased, so they will produce the lower polarization fractions. So let's back to this slide. So if, for example, in here, so if we consider grain growth and the aspect ratio become the third one as the K of isotropic, so we predict everything will be low, we have the lower polarization decrease and the perfect alignment model here, they can reproduce the animal observation. But the question again is that why grain can have the perfect alignment even in the envelopes and inside the disc. And the aspect ratio, actually aspect ratio is not affecting to how well grain can be aligned with the magnetic fields.
So can I think about your models as there are curves that can be moved up and down just by changing the aspect ratio? Okay.
Yeah.
Okay. The last question is in the second part. I'm not quite understand why the time scale is so short. You are all under consideration. It's only
50 kilo, you mean this one?
5 years to 20 years. So
This
why you consider?
Yeah, so the reason why I consider the 5 years and 20 years is because in the low intermediate mass protostar, we expect the high total luminosities when we have the accretion burst event. But the accretion burst events, they can last for the few days up to the maybe 10 to 20 years, and we do not know exactly what is the length of the accretion burst. And yeah, so that's why I consider different value of 1 year, 5 year, 20 years in order to understand if the accretion burst happen very long. So how strong it affect into the dust polarization. And if it only happen last for example, 1 year, 20 years, so how last of dust population inside our flow will be affected by that.
Thank you.
Yeah.
So, sorry, Haya, very great work. I mean, impressive work and very good talk. So I have two comments. Basically, the first thing here, just practical. When you show the plot, the unit, please use at least two values. For example, the color scale here, you just show one value, so we don't know.
Yeah. Because I put this one. I'm sorry. This actually you have two value here, but I put this one here so that hint the number.
I mean,
Sorry.
general comment is that the next science comment that recently they have the group in France.
Yes.
In astrochemistry group.
Yeah.
They use ALMA to observe a lot of protostellar force. And they use the different ALMA band. They calculate the beta index, the emissivity index.
Yes.
And they found that the grand side beta very low in the outflow cavity.
Yes.
It's very consistent with your recent work.
Yeah.
And my comment is that from your model also, please show the beta index from your simulation corresponding to it's really extremely useful to observer because as the observer, the people will calculate the value and that will have a lot. I mean, and also we can have what kind of porosity will be to have the small grand cavity wall or large grand cavity wall, and it will be very useful.
Yeah. Thank you a lot for your suggestion. So actually, the reason why I do not provide the dust opacity the spectral index inside this, because in the dynamic approach, so I just assume that gas and dirt are coupling together, and I calculate only in the 2Ds. So we know the gas velocities, so we assume that grain velocity is coupled with the gas velocity, and they should move in the one direction. But in fact, the last grain they will be easier to be decoupled with the gas, and they feel the stronger centrifugal force. So the last grain they can be decoupled from gas and immediately crash into the envelopes. But as using just the gas velocity in the embedded simulations, I cannot do this. So that's the reason why I cannot produce the spectral index in this study. But in the future, if we can, so where the one group in the Japan's Tsukamoto, they perform the coevolution of dust and gas in the embedded simulation. So if we can incorporate the RASTI into these models, so this model grains only, they consider grain growth by coagulation only. So if we can consider RAS into and then perform how dust grain they uplifts and then they move outwards. So I think we can predict how the dust spectral index they vary along the outflow cavity wall, and we can test with observation better.
Thanks for a very nice talk. And I have a question about how did you select the AMAD observations and to compare it? And because have you tried to divide your AMAD data in different kind of luminosity and compare it with your model?
Yes. So actually, in this, we had the statistic paper of Logolek in 2020. So he collects the data from a lot of young stellar objects, but I classify only 10 class 0 and 1 young stellar objects. And they had the plots of the polarization fraction, how they vary with the normalized gas columnicity. So I just take the data, summarize and plot in here. So the data here, they include both the low mass and the high luminosity and also the low luminosities. But I think in the future work of Fung, so she classifies how the polarization fraction they change in the case that protostar had the low luminosity and high luminosities. And I think it's one of your interesting point is that in the core we have the higher luminosity, we have the higher polarization fractions compared with the lower luminosities ones. And in our models, in this one, what we expect is that we only can clearly see the difference in the polarization degree with the luminosity when the maximum grain size is smaller than 10 microns. Yeah, so maybe, yeah, it can imply about us that we have the different size distribution inside the different environments. And if the asynchronous model, they really works, so maybe it will help us to explain why in low luminosity we have the low maximum size, but in the high luminosity we have the higher maximum grain size. Yeah, I'm looking forward into the future work.
So that's I'm working with about those in the protostar in the Orion molecular cloud, and that's I also classify with the low luminosity and the high luminosity source. And so it's a very primary result, so that we found that so for the low luminosity, for the high luminosity, so that's it's steeper, the dependent is more steeper than the low luminosity, and I didn't go to the detail about the explanation of the result yet, so.
Thanks, Jiang, for a very nice talk. I have a general question regarding this fitting. Polarization depends on several parameters. So how do you balance between these parameters?
You mean this one?
Yeah, to get the best fit
Yeah.
to data.
So you ask how I can find the best, the
Because,
grain that can reproduce.
Yeah, polarization depends on the grain properties, grains
Yeah.
maximum size,
Yeah.
magnetic properties, and all kind of things. And it also depends on the alignment mechanisms. And
Yeah.
then, so how do you know that the contribution of alignment mechanism is so much and grain size is so much, so we can get the best fit to the data?
How I in the question is how can I get this data? So in the left hand side, so I assume that the same size distribution inside the core, the same luminosities, and what I change is just the number of iron atoms inside the each grains. So with the change in the number of iron atoms, so the grain's magnetic property will change. And when the grain's magnetic property will change, so it will change the internal alignment efficiencies and the external alignment efficiencies, and it will affect into the dust polarization in the last. So, and here I just plot different value to see which value they can reproduce the mass. And similar in this case, so I consider the same models. I assume the same model of the grain magnetic properties, same model of magnetic field, gas density, and luminosities, and just only vary the maximum grain size. The other two, and when we have the different maximum grain size, so we have the different alignment size range, so it will affect into the next polarization degrees, and that's why we have the different values. And when I overplot, I see that which value within the range of the mass. Yeah, so in order to conclude that, but in the real case, so I think at least the maximum grain size we can constrain, for example, by the dust spectral index or the talk of COA, like the increase of the polarization degree at the long wavelengths. So at least we can constrain about the maximum grain size first. So if we can constrain the maximum grain size, we know about the gas density profiles and luminosities by the dust continuum emission. So we can vary different grain magnetic properties in order to and try to find the best fit. So that's how we can, from the observation we can have to reconstruct again the maximum grain size, also the grain properties. And if we want to exactly understand the grain property inside each object, so I think we need to consider like case by case. It is one is just statistically.
Okay, yeah. Hello. Yeah, okay. So first of all, I would like to answer a little bit the question from Haifeng about why green drift is perpendicular to magnetic field. So of course, in the ambipolar diffusion case, grains are drifting across magnetic field. So, but in like on larger scales, like in molecular clouds or interseminiums, grains can also be drifting across magnetic field, perpendicular to magnetic field. This is related to the acceleration mechanism of dust grains by MHD turbulence. So for example, in the alphanic turbulence, the velocity fluctuation are perpendicular to the magnetic field. And the fluctuation of velocity of gas induce the electric field, E equal to V cross B. So electric field now is perpendicular to magnetic field. And this is the electric field that accelerate charge grains in the direction perpendicular to magnetic field. So that's why the grain drift is most likely across magnetic field rather than along magnetic fields in both MHD turbulence and ambipolar diffusion.
So the turbulence and the dynamics is very different between disk and the molecular clouds. Do you expect similar pictures in disk? As disk is where grains are growing from like tens of micron to 100 micron millimeter of pebbles.
Yeah, so we haven't looked into the details of the turbulence in molecular scales and disk scale, but what we assume here is the grain drift is always perpendicular to magnetic field. Of course, in specific environments, we have a different mechanisms that induce the drift across magnetic field. If we work with molecular scales, and then we will refer to the acceleration by MHD turbulence, and we have the same results. Grain drift is perpendicular to magnetic field. And on the protostellar core scales, now the ambipolar diffusion dominates. And then it also induces the grain drift across magnetic field.
Thank you.
Yeah. Okay, so also another question, I think I would like to elaborate the answer a little bit regarding the question from Diep. So the good or the key thing here is we have an alignment theory. So the Ambrad alignment theory now can predict the alignment degree depending on a number of parameters. So the parameters here is iron inclusion and maximum size. And we use a theory and then we predict the alignment degree. When we change the maximum size, when we change the iron inclusion, and then we get alignment degree from the theory. So the fact that here, why we can get these parameters that fit the data, because Zhang did a lot of work. She played with many parameters. And here we show only the best one. We have many other models, and then we show in the appendix. So this is the best one. Of course, this slide is a result of 2 years work, 3 years.
I don't remember. Actually, this work, I think it starts from the beginning idea, I think it's 2021, but after that, I worked on implementation in the Polaris, so it takes longer times, and work on this, and after that, we haven't incorporated the inelastic realization at this moment. So after I get the first results, on the result, it does not match. So they only match in the envelopes in the left hand side, and on the result in the envelope, and this is on totally mismatch. So we think that might be the inelastic realization may work. So that's why we try to so we try to implement inelastic realization and try to rerun everything one more time with a different value of inelastic realization. And very luckily, it's like provide ready rather well reproduced amount sufficient. Yeah, but this is just for the 10 statistically for 10 young style objects, but in reality, we have the many kind of young style objects and everything is different. So yeah, but this is potential mechanisms, but want to test more so we can work more on the different objects.
Can I have a technical question here? So I see in the plot so that the beside the trend that is always degree with the density. So we see that at the place at about the density of about 0.02. So you always has a degree of polarization fraction.
Yes. So the reason for this is, for example, when you see here, this is the distribution of the polarization degree maps. I plot in the H-on direction, and this is the outflows. This is the disk outflow cavities and the inner envelopes. And the reason shows the decrease is in this area.
So it chances in
chances. Yes, because in the envelopes here in more the initial turbulence. So the magnetic field have the outer shutters really clean. When they move when we have outflows, so when the outflow launchings, so it will create also the helical magnetic field in this direction. We have the not only perpendicular component, but also the outside component. And that's why it's the shortened during the polarization fashion in this area because of the magnetic field in outflows and the magnetic field in this direction in the envelopes. So that's why it
Suggestion. So now, if you confirm that the transition is
Yes.
caused by the radical change in the magnetic field inclination angle,
yes.
so we can use a deep feature to probe the magnetic fields, right? Because you from the observation, you can plot P versus N, and then
Yes.
this is a location where you have a transition
Yes.
in the polarization slope,
Yeah.
and then it is due to the twist of magnetic fields.
Yes.
And then
Yeah,
so,
yeah,
so
so-
that it can be used to
Yeah.
constrain the
Yes.
magnetic fields.
Yeah, so in this case, we can do this. But just the question for Siwei is that when we observe the many glass young style objects, whether we always see this dip or just the flash continuous reduce. What I mean is, in observation, whether you see this dip in the observation in many objects. Yeah. So what I mean, previously Phương asked the question why in the polarization with the gas luminosity instead of the continuous degree like this. So we have the it decrease and then it slightly increase and then it decrease again. And I explained the dip in the polarization degree here is because of the change of the magnetic fields by the outflows. But what I want to ask is that when you observe the young style objects, whether it change is present in the every objects or not. Yeah. Yeah.
Yeah, maybe next time we Okay, so I think that we can wrap up this session now, and now we have a coffee break for 20 minutes. One more question. Yeah, so we can discuss in the discussion session. Yeah, and so that's please come back at I think that's 11 is 11 is okay because so today's schedule is not very tight. Thank you. Yes. So you speak to the mic. Yes. Can say again. So hi everybody, welcome back. So the section before lunch today will include an review talk by Dr. Haifeng Zhang from Lijiang University in China. He is going to talk about the dust polarization in protoplanetary disk, cell scattering, range alignment, mystery, and magnetic field, plus everything. So that's the Haifeng. You have 40-minute talk with 35 minutes for presentation and 5 minutes for the Q&A. Yeah.
Hello. Hi. Good morning, everyone. Thanks for the invitation, and it's very my honor to give a talk here on this polarization from disks. So it's a very different topic than what we have heard yesterday and so far. So I hope you enjoy it. In the right is the canonic image taken with ALMA. This is the HL tau. This image reveals recent gaps which revolutionize the field of planet formation. Through a glass, we can see a lot of polarization vectors. What we can learn with this kind of polarization vectors will be the topic of my talk today. Yeah, so I think I don't need to explain in more detail on what's happening on a large scale. We see a lot of magnetic fields, and there are some excellent talks so far already. We know that the disk stars are formed out of magnetized clouds. And when we go down to envelope scale, super bright, sorry. When we go down to envelope scale, we also see a magnetized, and this is one of the textbook example showing hourglass shaped magnetic fields. However, we would very much like to study the magnetic fields on the disk. So we use the 7 millimeter polarization to look at the disk. This is HL tau is also is the first image taken with polarization. And this is what we see. Back in the days with Karma, we got the polarization, we got the magnetic field detection in this system, which resolves as a uniform magnetic field structure, so along the major axis of the disk. This is not physical. So 3 years later, we got an improved image with ALMA. So I will just talk over that. So what is the origin of that? We know that if you use the magnetic field to interpret this polarization, you would imply a uniform magnetic field. This is unphysical because if we know the disk is differentially rotating, and if you put this kind of magnetic field configuration into a disk, it will wind up into toroidal configurations very quickly. So we believe it comes from not magnetic field, not from dichroic thermal emissions of dust grains, but rather it's from the scattering. This is how it works. So here is a daily life example of scattering producing polarization. We take a full sky image with a fisheye camera, and we apply a polarization filter that only allows light with polarization in this direction to come through the camera. And you will see a dark lane across the thinness. This means that light scattered in the atmosphere are polarized, and the polarization is perpendicular to the light coming direction with the sun to the right. And also we can see that there is a strong angle dependence of polarization, and the polarization is maximized if it's scattered by 90 degrees and goes to a lower value to 2 ends. And this effect was first pointed out by Kataoka in 2015, in which he studied the polarization of a tube. This is the infinite cylinder. And you will see that because the dust thermal emission inside the cylinder is mostly along the cylinder. And after scattering of such radiation field, the polarization in the cylinder is perpendicular to the cylinder, perpendicular to the structure. And if you go away from it, you will see a transition of polarization from perpendicular to parallel to the cylinder. And he also studied a polarization in a transition disk with a quiescent structure, which was not sure, sorry. I will show it later. So this is how it works in an inclined system. So imagine we are that screen sitting in a disk, in an inclined disk. We receive radiation from all directions. And for light coming from the major axis, they are scattered by 90 degrees, which produce polarization along the minor axis. However, for light coming from the minor axis, the scattering angle is 90 degrees plus and minus inclination angle, and they are less polarized and polarization is along the major axis. When you add all of them together, you are left with a you are left with some polarization along the minor axis, which applies to a large fraction of the disk. So what you're left with is you got a uniform polarization pattern in the disk just coming from the scattering of dust grains, thermal emissions by dust grains themselves, and because of the inclination of the system. And after our work, there's many, many systems. These are some of the best resolved ones. At ALMA band 7 in TITARI class 1, class 2 systems, we almost universally see this kind of uniform polarization patterns. And they are indicative of 100 micron dust grains. Yeah, so there has been, it is very sensitive to grain size, and there has extensive work on it. I'm not going to spend too much time on this topic, but if you are interested, we can discuss afterwards. I would like to mention one work is, one of the direction that was studied mostly along this line is the porosity of dust grains raised by Ryo Tadaki in 2019. He showed that if the polarization, if the dust grains are not compact, you will see a broader response window for the grain size and wavelength. But at the same time, polarization fraction is lower, so much that in the Shangjia Zhang's work in 2023, they argue that the grain size in the H tau system has to be 1 millimeter in size, and the porosity is like 0.9 to 0.7. Yeah, so now, in addition to the grain size constraint, it is also very sensitive to the spatial distribution of dust grains. In this case, we consider a optically thick and geometrically thick system. It is optically thick so that dust grains only receives light in its nearby neighbors, and it's only sensitive to local structures of dust grains. It is sensitive to local structures so that in the near side and the far side, the polarization is determined by the local inclination of the disk surface. But if just by looking at this image, you can see that the local inclination angle is different between the near side and the far side. More specifically, the inclination angle in the near side is larger than the far side of the image. So this will result in a higher polarized near side than the far side, as we show this in these simulations. Right. So 6 years after our observation towards H tau at lower resolutions with, I think it was C7 ALMA configuration, we got a much higher resolution image with ALMA again. This is like there are over 1,000 independent vectors in this image. It is very has many, many details. And the most striking detail, of course, is the transition of patterns from the uniform patterns on the larger scale to the azimuthal patterns on the first string, on the first gap. Sorry, I will go to details about this kind of azimuthal patterns in more detail later. I would like to note that it is similar to what we see at ALMA band 3, so which is indicative of grain alignment and indicative of either magnetic field or either from the differential motions of gas dynamics. I will go into detail in more detail later, but let's stay to the picture of scattering first. In addition to this kind of transition, we also see that in the very inner disk, even though the polarization factors is mostly along the minor axis as what we see in scattering-induced polarization, you also see a very strong near far side asymmetry. So if you use the previous picture, you will see that the near side is brighter than the far side, which is seen in the data. And in order to produce this significant asymmetry, you must need a significant difference between the local inclination angle between the near side and the far side. And that will require the dust to be puffed up in the inner disk. And we did a series modeling and show that if you are using a very thin inner disk like HOR of 0.05, you don't really produce this kind of near far side asymmetry. And you really need a model with HOR of 0.15 or larger to reproduce some extent of this near far side asymmetry. Yeah, we conclude that in the inner disk, the HOR is 0.15 or higher. Yeah, so let's move a little bit larger scale than the inner disk and go to the first ring of the system. This is what we see in the polarized intensity in the first ring. You can see that the polarization is higher here along the minor axis than there along the major axis. This is what you will see with a simplest scattering-induced polarization picture. You will see a rather uniform polarization patterns across this first ring. In order to understand what is producing this kind of azimuthal contrast in polarized intensity, we need to go back to the very beginning of this picture, in which you have an infinite cylinder. In this kind of cylinder structure, you will produce polarization perpendicular to the local structures. And instead of this kind of, I have this plot here. So this kind of transition was seen in HD 14, 25, 27. The transition from the radial direction to azimuthal pattern. So yeah, now we have two scenarios that produce different polarization patterns. For inclination, they tend to produce polarization that is uniform along the minor axis of the disk. For the anisotropic radiation, you are producing polarization that is perpendicular to the local structures. In this case, in this case, we have a quiescent structure, and the polarization is perpendicular to the quiescent structure, and this is what you will get from the radiation anisotropy. And the interplay between these two strongly depends on how much radiation you can see from the dust grain. If the system is very obliquely thick in the midplane, you don't see too far across the midplane, and you see mostly the scattering-induced polarization. But if the radiation is puffed up, if the dust grains are puffed up and not settled, you will see very further away along the midplane, and you see more of the left scenario, and you will be able to observe a different polarization patterns. So this idea has been explored in many systems. For example, Hashi and Kadoka studied the F-settling parameter and conclude that F-settle has to be 10 or larger, which concludes that in this system HD 16, 25, 27, oh sorry, I forgot the phone number. But in this system, the dust are moderately settled with F-settle of 10 or more. Daniel Lin also studied a different picture that put everything together, that they show a near far side asymmetry in the inner part, and they show transition to azimuthal patterns at the far side when it's becoming obliquely thin. And you see a uniform pattern in between in the oblique thick regime. So in this system, in the IRS-48 system, we observe very high resolution polarizations, and the polarization is mostly along the azimuthal part, along the inclination. So although this is not a full disk, we know the inclination, and this is perpendicular to the minor axis of the inclination. And but you do see a radial contrast in the polarization fraction. The inner part is more polarized than the further part. And we did a series model showing that if the dust grains are not settling at all, you will start to see the azimuthal pattern at the outer part. This is not observed. But if the dust grains is well settled, the polarization fraction will be rather uniform across this whole crescent. You need some moderate settling to explain the radial contrast of the polarization fraction. So which gives us that the settling parameter is about 2 in this system. And you can even translate that into the turbulence that so in this system, the turbulence is on the order of 10 to the minus 3 to 10 to the minus 2. This is moderately turbulent. And this kind of constraint can hardly achieve without polarization observations. Although this is a vertex, so if vertex being turbulent is almost a trivial conclusion though. So let's go back to this system. In the first ring of HL tau, very high resolution polarization, we see more polarized light along the minor axis than the major axis. If you use the scattering-induced inclination polarization from inclination, you will see a uniform polarization patterns across this whole ring in the left. However, the radiation isotropy is producing polarization perpendicular to the structures. This is like a cylinder, but it's banded into a ring configuration. It is producing polarization that is perpendicular to the structures everywhere. In reality, you need to add them together, and you see that in the minor axis here, these two mechanisms is producing the same polarization patterns, but in the major axis, they're canceling out each other, and resulting in what we see in these azimuthal patterns. So you can then change the aspect ratio of this first ring. You will see for well-settled ring, HOR of 0.01, you will see uniform polarization patterns across this first ring. And in order to produce the observed value, you must need a HOR of 0.1. And this is how it compares with 4 quarters. I'm not gonna. And the HOR of 0.1 agrees with the observation very well. I will skip this part, but basically, because we don't see any near far-sighted symmetry on large scales, it puts some constraints on the large scale aspect ratio, and we say that HOR is smaller than 0.05 on larger scale on certain AUs or larger. So if you put everything together, these are the constraints we got. So we see a HOR of 0.15 or higher in the disk, 0.1 in the first ring, and is smaller than 0.05 at large scale. And these are 2 previous constraints. This constraint from the band 9 observation that they see some near far-sighted symmetry in the total flux. And this is constraint from Christoph Pont that they measure the sharpness of gap across the ring and conclude that the disk must be settled on 1 AU or smaller at a 100 AU scale in order to explain the observation. However, if you try to cross all the constraints with constant turbulence alpha, this is alpha of 10 to the minus 5, and this is 10 to the minus 3. None of them can reproduce the result very well. If you want to put everything together, you need a structure that has a varying turbulence alpha. And the alpha is 10 to the minus 2 on the first ring and the inner, and it goes down to 10 to the minus 5 at a larger scale. So the turbulence is varying as a function of radius. And more importantly, because this HOR is 0.1 in the first ring, it puts some limit on the planet formation there. But what are the implications beyond that, and what is causing this high alpha is still under investigation. Yeah, so I would like to summarize the first part a little bit. In the first part, I discussed the scattering-induced polarization mostly. And we discussed that the scattering-induced polarization, this kind of uniform polarization patterns are almost ubiquitous in protoplanet disks, especially at Alma band 7. And this is a very powerful tool to study the grain size, to study the vertical settling, or even the composition of dust grains, how porous they are, or even they are sensitive to whether it's silicate or carbonaceous. Okay, so what about magnetic field? And this is where we start with. We want to study magnetic field in disks with this kind of observations, but we end up with getting a lot of scattering, and we study all the grain size properties with that. But what about magnetic fields? So beyond the scattering, there are some cases that we believe they come from grain alignment. For example, this is some of the best examples. In the Alves paper, they studied the BHB's 0711 system. And at different wavelengths, at band 3, 6, and 7, you see a consistent polarization pattern across 3 bands. So this is not what you see in scattering at all. And more importantly, the polarization fraction is higher and higher as you go to longer and longer wavelengths. This is also not scattering, what scattering will produce. So we believe in this case, we are getting some green alignment. And they are claiming this is from magnetic field, but I'm not sure. Don't know it for sure. This is another system in the HD 142527. I discussed that in the northern part, we see a transition of patterns from azimuthal part to radial part, which is indicative of scattering. However, in the southern part, there are 2 differences. One is the polarization fraction is much, much higher. In this region, the polarization fraction can be 12%, I think, at band 7. And they believe they come from aligned dust grains that are much smaller than the wavelengths that we're looking at, maybe 10 micron to 100 micron somewhere in that order. And they're coming from toroidal B field. So earlier this year, they published more data on this system. In addition to the band 7 observation, they published 6, 4, and 3 observations. And you see there are some changing of patterns in the northern part, but the southern part, the polarization pattern is consistent across different bands. And this is indicative of polarization from green alignment and not scattering. They go deeper into the diagnostics, and this is the polarization. This is the inferred magnetic field direction in the southern part. And you can see, indeed, it is mostly toroidal magnetic field, but you see a difference in the position angle between the observed B field and the azimuthal B field. And this is what they got. So first of all, you can see they have a 10-degree systematic shift from zero. So which means that the B field is not completely in the azimuthal pattern, but has a 10-degree twist to the toroidal configuration. But more, they go even further, and they identify that the system has some structures that the position angle difference goes up and down, and there's a transition point over here, and they believe it comes from some non-zero BZ component, and they use a single layer model and show that in the epicenter of the disk, we expect the polarization to change its delta B phi in one manner to another. So from this small peak, they are able to give a constraint on the BZ. So to sum up, there are 4 conclusions from this work. First, thermal emission from aligned grains indicated from the consistent pattern across different bands. Also, the green alignment are due to B field. They gave a BR over B phi of 0.26, and they gave a D space over B phi of 0.23. But I would like to remind you that the trustworthy and I would believe more on the conclusion from the top and less to the bottom. It's like a pardon? The color represents different radii from the center. So the blue ones are like inner part, and the red part are outer part. Yeah. So in addition to that system, we have a lot more data in the field. Among all of the patterns, especially observed at band 3, the most common pattern is the azimuthal pattern. I would like so there's one caveat. Azimuthal pattern is not universal as uniform pattern at band 7. We have a bimodality in band 3 azimuthal patterns, but let me focus on azimuthal patterns here from here. So we see a lot of these kind of azimuthal patterns at longer wavelengths. Some of them are not so long, like band 6, or even you see this in band 7. This pattern was initially proposed by Tazaki that they are coming from the K-ret, that the radiation are aligned in the dust grains, and the dust grains are aligned such that they have short axis along the radial direction, and the azimuthal pattern will be produced by azimuthally aligned dust grains. We did some investigations into this system, and so this explanation has some problems, especially in the azimuthal variations. If you take a system, here are, for illustration, I put 8 dust grains that are oblate, that are aligned with radial flux. And as you see, when you start to incline this system, for all the dust grains along the major axis from left and right, the aspect ratio from to the observer remains constant. But for the aspect ratio of dust grains along the major axis, along the minor axis, it appears as round, and they are less polarized. The result of that is if you use radially aligned dust grains, they are more polarized along the major axis than the minor axis. This is not what you see in the data. But we propose a different scenario. In this case, we have dust grains that are needle and prolate, and they are aligned with some azimuthal field. And if you do it this way, you will see that the dust grains along the minor axis stay as needles. However, it becomes round as you go to the major axis of the disk. The result is that the dust grains are more polarized along the minor axis than the major axis. We believe this pattern, together with scattering, can produce this kind of azimuthal patterns. And we think the dust grains are some sort of prolate grains, azimuthally aligned prolate grains in the system. This is the agreement. But what is the origin of that? So in our original paper, we proposed that maybe it is due to the differential motion between gas and dust, similar to the manner of Gould mechanism. However, Gould mechanism is known to only work in supersonic scenario, where the differential motion can hardly achieve that velocity. Yeah. So recently, Daniel proposed a very different scenario that he called it badminton birdie-like alignment. It's like you have a badminton, you have a solid top and a fluffy tail. And if you throw it, it will just be aligned along the velocity of its movement. The reason is that, so if you have a massive top and a larger tail, because it receives a lot of wind in this direction, and the restoring torque will push the system so that the system has minimum energy when it's moving along the flux. Yeah, here is how it works in the phase diagram, where all the dust grains with some damping, they will eventually go to the alignment of the as it being along the drifting direction. However, this is some oversimplified model. We discussed a less simplified model in which we don't really have this kind of two spheres, but rather one single oblate. But in this system, the mass center of the system is displaced from the geometric center. And if it's displaced along the longer axis, the dust grains will be just aligned in this direction. And displacement only need like 1% for this to do some work. So it's possible that this kind of badminton birdie type of alignment is doing the job to produce this kind of azimuthal pattern. There's another work done by Tim and his student Song and Professor Deb. They discussed the wrong internal alignment. So in this case, it is still magnetic fields doing the work, doing the job. But so the dust grains are aligned with azimuthal or toroidal B field. However, the dust grains do not have correct internal alignment. They are aligned that they have their long axis being aligned along the B field. So it's exactly the same scenario as we're discussing. So this is also a very interesting alternative. Yeah. So along the story idea of azimuthally aligned prolate grains, there has been many works being done. For example, Mori and Kataoka studied the oblate plus scattering and prolate plus scattering, and they think this reproduce the data better than so the prolate plus scattering is better than the oblate plus scattering. And Daniel also did the work on the interplay between the scattering and the isometrically aligned prolate grains. And you can see a transitional patterns at different optical depths. I would like to note that both of these works has their limitations. In this work, they are limited by treating the scattering as scattering by non-aligned spherical grains. So they can emit polarized emission, but the scattering is treated as if the dust grains were spherical. And this work is done under the plane parallel simplification. It is scattering by aligned grains, but they are only they have a plane parallel model behind it. So we put them together. Here we show all the wavelengths. At band 7, we see uniform polarization patterns from scattering. And band 3, we see a polarization pattern that is azimuthal. So qualitatively, we have a transition of polarization patterns, and which is the result from the transition of optical depths. In optical thick regime, the scattering dominates, and you see all uniform patterns. And in the optical thin regime, you see some sort of alignment. Oh, okay. So that if you assume grains are aligned this way, you will know the azimuthal variation of the polarization for both scenarios, and you can decompose these two components, and then you got this result that so the solid line is the contribution from the scattering, and the orange line is the contribution from the thermal emission. I would like to note that even though from the data we got this kind of contribution variation as a function of wavelengths, I don't think there's any dust model that can produce this kind of the variation. So there's a long way to go. Yeah. So previously we were talking about transition of multiple bands. We also see this transition from the uniform pattern to the azimuthal pattern between rings and gaps. So this is the model that we have azimuthally aligned dust prolate grains everywhere, but because the optical depth is different between the rings and the gaps, you naturally get the transition from the uniform pattern in the rings to the azimuthal patterns in the gap. So in this model, we assume grains are aligned everywhere, and it's azimuthally aligned prolate grains. Okay, so here is more like a question than on description than answers. I don't have answers. In addition to this overall azimuthal patterns, we have some system that see some systematic variation. For example, this one is not quantified. In the GG tau, Tang got a 9-degree twisting, and in AS209 they got measure about 4-degree. And back in the HD 14, 25, 27, they have a 10-degree, if you remember the variation. So Kataoka had the idea that if you have this kind of aerodynamically aligned, it's like mechanical aligned dust grains, so that the dust grains are aligned with long axis perpendicular to the drifting velocity, you may get this kind of patterns. However, in order to get this kind of twisting patterns, you need Stokes parameters to be as large as 1. And in the disks, I think this means that grain size is like a centimeter or 10 centimeter. That is way beyond current consideration. So this picture has this kind of caveats in it. So it's not a perfect picture to explain what is going on here. Here's another interesting example. So we have a high resolution observation towards the L1447-48 system. In this system, we see 3 mechanisms that are in play. So in the close to the stars, these are 2 stars. So yeah, we have some sort of uniform patterns here and here. They are likely dominated by scattering. And on the larger scale, you see in general some sort of hourglass shape. Or not, it's hard to see. But we conclude that this comes from the magnetic field, likely dominates. But in between, interestingly, we see some sort of polarization patterns along the structures in the dust density. Maybe it's because of motions between gas and dust, or maybe it's because of magnetic field being perpendicular to these kind of structures. We don't know. Yeah. So last but not least, I would like to discuss a new technique we proposed. So because in the mid plane, we have the gas density is very, very large, and the grain size is also very large. Both of them make the grain alignment efficient in this mid plane. So we think if you go slightly above the this mid plane to the disk atmosphere, we are talking about near infrared observations towards disks. And in this wavelength, we are working with micron size grains. And also, because it's 3 to 4 scale heights above this disk midplane, the gas density is reduced by a factor of 10 or larger. So it's possible that grains in the disk atmosphere are aligned with magnetic field. But in this study, we assume that grains are aligned with some sort of magnetic field. And this is one case that you see scattering of scatter light by grains aligned with magnetic field will produce this kind of black vectors. They are making an angle with the red vectors, which is canonically assumed polarization direction that is perpendicular to the light incoming direction. And in this somewhat extreme case, that inclination angle is 60 degree and the phi b is 90 degree, that has a large toroidal component, you see the polarization reversal as polarization being perpendicular to the radial direction. Oh, okay. So this effect is more efficient for a toroidal B field and for more inclined systems. And we also studied the Q phi and the U phi. These are the observables in this kind of studies and observations. We show that the U phi can be as large as 15% polarization in the U phi. And we have a less, we also, in the paper, we also present a less extreme case with 45-degree inclination angle, and you don't have polarization reversal, but the U phi is about 5%. That is still observable. This is one case that may be indicative of grain scattering from grain alignment. It has a positive U phi everywhere. This kind of U phi cannot be produced unless you have aligned dust grains. If you have spherical dust grains, you can do multiple scatterings, but you won't be able to produce this kind of U phi. But it will be a natural outcome if you have twisting B field. Right. So we have a transition here. You need, if you want to study the interplay between these two, you need to study scattering by aligned grains quantitatively. And yeah, I will just go very fast, sorry. This one is also scattering by aligned quantitatively. But if you want to do the scattering by aligned grains quantitatively, it's going to be very hard because there are so many angles. If you want to tabulate the scattering by aligned grains, you will need 30 gigabytes of lookup table, which is impossible for any numerical code to do it. And also, if the grains are large, the optical properties will be very expensive to do it on the fly. So we propose it to do it with numerical network, and it is doing reasonably well. These are the neural network performance between the real and yeah. And we are putting this into a new Monte Carlo data transfer code, and the code will be GPU based. With that, I will take any question. Sorry, it's going very fast towards the end.
Yeah, okay. So I think it takes some time. Yeah, so I have one question about the Brolet shape. So it seems that the Brolet shapes provide a very good fit of the polarization to the azimuthal pattern.
Yeah.
But in fact, in this model, you don't consider the grain rotation.
So
because the grains are always rotating. So if the oblet shape, if the Brolet shape is spinning around the long axis, it is still Brolet shape. But if the Brolet shape, if the oblet shape is spinning around the long axis. On average, after the rotation, it will become also a brolette shape. So it, but in the case of oblet shape, is spinning around the minor axis. It is, yeah, of course, it's an oblet shape. So there's a degeneracy in observation point of view.
So yeah, you're right about this. Thanks. I will give some time to clarify on that. Whenever we talk about oblet grains, we are talking about grains aligned with short axis. Whenever we talk about pearlite grains, we mean grains aligned with long axis.
Oh,
We're not implying the exact grain shape.
Oh, okay. So it's not the physical shape.
Not the physical shape.
Okay.
Right. Because if the grains are aligned with short axis along some direction, it can be precessing, it can be cannot or not. But in terms of ensemble average, its optical properties will be effectively like the oblet.
Okay.
And it's the same for pearlite grains. Yeah.
Yeah. Okay. So maybe it would be more clear if you mention this is like a effective pearlite shape.
Right.
Thank you.
Other question?
Hello. So recently, some teams suggest that maybe the molecular polarization is another tool to problem magnetic field in protoplastic disk. But since the emission from molecular can still be scattered by the dust grain, so I'm wondering whether self-scattering could also affect the result from the line polarization.
Yeah, we had that idea long ago, but basically right after my graduation. But we didn't. It's possible, but we didn't do any quantitative analysis on that.
Okay.
Any other question?
Yeah, I think one potential way to probe magnetic fields in the disk would be waiting for SKA.
Okay.
Because you see, in a longer wavelength, it is like optically thin, and then also it's now is the magnetic fields or the alignment would be dominant, as you see in the optically thin case, in optical thick case. Yeah. And also, actually, I think from the synthetic polarization modeling, Zhang, we show that the polarization degree increased with wavelength for the protocellular disk case. So it's quite similar to what you show here, the polarization increased wavelength. Yeah.
More question and comment?
Regarding the Birdie-like model, do we have any evidences for this kind of model? Anything?
Which one?
The Birdie-like.
I don't know. I mean, to me, the paper has some still theoretical work to be done, and there's some. For example, the time scale is not quite clear, and there's some simplifications in the Daniels derivation, and whether it still holds, I'm not sure. But so if you want to talk about observational evidence, the IL-1448 was one that we are thinking about. Yeah, for example, the polarization being along the streaming. So it's like along the differential motion. But I think the problem with grain alignment mechanism is, I feel it's very hard to definitely say how they are aligned. We can only tell whether it's from aligned or not.
Yeah, it looks complex.
Yeah.
Okay, thanks.
Yeah, I think we can continue the discussion section now, so you can have any comment, and there's a discussion for the whole the morning section. So don't hesitate to to raise any comments or the other remain things that you want to discuss.
Yeah, I think in the paper here, The polarization angles are aligned along the gas streamer, right? The recent paper by Looney et al. Yeah, yes, so that one. So it seems that the polarization angles are aligned with the streamers. Yeah.
It's not necessarily a streamer. We are looking at the dust continuum. So it's, I would say it's aligned with the
density structure of filaments, yeah.
I don't know. It may not even be the filaments you're talking about.
Yeah, I think in the paper, the explanation for that is alignment by mechanical flows, something like that.
So it's like, it had a pretty like.
I think because I think because here the density, what is the gas density in the inflow? Maybe it's not very high. So we show that mechanical alignment would be important in the mid plane of the disk, where we have very high densities. So the gas pressure is higher than radiation pressure. But in this environment, I think we still have a radiation. So radiation pressure may dominate over gas pressure. So even grains are subject to both mechanical torques and radiative torques, but the radiative torques are still more important. And then we need to quantify like whether the alignment is driven by mechanical torques or radiative torques.
Also, the dynamics in this system is very complicated.
Yeah, the dynamics. So one more parameter is a time scale. So in my general theory, we have to check the time scale. If the dynamical time scale is short, so grain alignment is not fast enough. And in this case, the alignment may happen along the radiation direction of gas flows. In the like a molecular clouds ISM, we have a loss of time. So grains can be efficiently aligned at high J, but when grains have a very short lifetime. So for example, initially grains in the inner envelope, smaller grains in the inner envelope, they are not aligned. And then they follow the inflow motion. And during this time now they are subject to radiation or gas flow. They start to be aligned. But the process for alignment takes time. So if the flow is very fast, and then the grains do not have enough time to be efficiently aligned, and then they may have a very quite different alignment picture than what we know in ISM or in the star forming region. So one more parameter here is a time scale. Yeah.
As a comment. So if not, so I do not have enough time to prepare something for the discussion session, but during the talk, so I have some note and maybe I can share with you for the further discussion. Let me see. I think I need the authorize from the host to share.
Maybe I can ask something.
Yeah, I can. You forget all the below because it's my internal notes for the workshop. So that was for the for this morning session. So we listened about the bipolar diffusion magnetized effects, the disk size, and also the RASD model. Even and there's several things that we discussed. But here I just catch up some of them. And so I think that's the ones that I want to pay more attention here about the polarization percentage depend on the luminosity of the source. So this morning Zhang presents that. So if in the protostellar core with the grain size greater than 50 micrometers, so it does not depend on the luminosity of the source, right? And if the grain size smaller, then it will depend on the luminosity of the source. So I think that's the one interesting that we think we should test, because so you present in the morning, that's with the 50 micrometer grain size, so it very fast disrupts in the time scale of 5 to 20 years to how small it is, I do not remember.
So, um, so it's also depend on the luminosities. So we found that how to say. So we found that the rest descriptions only happens when the cellular luminosity is larger than the pi absolute luminosities. So, can you repeat your question?
I mean that's for the disruption. So that's it's very fast, and then so that go to the with the minimized grain size can be disrupted. So that's yep. So you present that, so that's the first you confirm that so for the object is greater than the phi luminosity. So then it have strong radiation field, and that the rad-D start to active. And so that if the grain size in the source is very large, so it's more efficient for the rad-D. And so that's it is true that so it can disrupt until the 10 micrometer and it stops. So why? Because so if it grain size smaller than 10 micrometer, and then so it does not depend on the luminosity of the object anymore.
Actually, it also depends on the time scale that grad can be activated. So even without that, if the solar luminosity is greater than the 5 solar luminosities, so it can quickly destroy very large grains in the outflow base. So the outflow space, the scale is just around the 1 to 200 AUs. So if it happens, so it will prevent very large grain in in this area. But the time scale, so usually we have the high luminosities when the accretion burst happens, but the accretion burst event, it can last for a few days or to maximum is just 20 years. Yeah, so in the case that it cannot, so when it activates, it can like temporarily prevent very large grain to enter the outer regions, but after that, when it terminates, so large grain still can be ejected outwards and present inside the inner envelopes. So
Thank you. So the second point is that about I found it's very interesting, the transition between the envelope and the protostellar core on the polarization quotient pattern. And so I think that's here I see that this morning that's the Siwei and Ngọc saying that so you have a project related to the B35. I think it's very promising to test what the two mechanism.
Actually, for actually, if we can also test the rad-D if it happened or not or something like this. Yeah, but for the B335, we also see that the morphology is the same or wavelength, but the polarization fraction is changed, and the curve of the wavelength is quite the same, but the fraction is changed from region by region. It may be because of the asymmetric change or elongation change, something like that. Yeah.
You mean the reason by reason, you mean by the
Yeah.
scale of the source, or by the scale of the source from the outer to the
from the outer to the inner.
Yeah, because so that I see in the morning, Zhang, so that from all the data that she collected from the GUELEC, so we do not see that pattern properly. It's because of in the GUELEC, it do not go to the very fast in the outflow or envelope.
I think it's in the observation of GUELEC, they collect a lot of the young-style object around the 10s, but each object has a different inclination angle. So for example, what I mean in the sample of the GUELEC in 20 and 20s, so they collect a lot of the young-style objects, and some of them they observe in the edge-on, but some of them they can have the different inclination angle. So when they average on, so it plus it continues like this. But if on the objects, it observes in the same on the edge direction, so maybe we see this dips. And the reason we see the dips in the simulation is just because we take the one snapshot in the edge direction, so that's why we see the dips.
Can you include the inclination correction to the code?
Yeah, actually, I can try to change the viewing angle to see how it's affecting to the polarization change with the gas column density. But I think I have not yet done this. I have not yet tried this. So yeah, I can try to try to see if we look on MOSFET ons or in inclination of 45, whether we still see this dip due to the transition of the magnetic field or not.
Other comment?
Can I?
Yep.
So I have two general questions for the studying the manifolded in disk structures. So as we showed before, there is a lot of mechanisms are related to the disk polarization. So I wonder, is there any good way to distinguish which part is the self-scattering and which part is mechanical things and which part is caused by manifold? And second point is in the disk regions, it is hard to apply the D-shape method and it has toroidal fields. So I wonder which method is good to estimate manifold strengths in disk structures.
So sorry.
It's different
Yeah.
of the mechanism in the case.
I'm sorry, I'm applying administrative process in our university. It's so sorry, can you repeat your question? Please?
Yeah, so in disk, the dust polarization is caused by self-scattering and mechanical alignment and manifold. So when I saw the papers, they said that which part is shade and just to say that this is affected by self-scattering like that. But if there is no shade, I cannot distinguish that one. So which the specific method to distinguish the effect?
Yeah, so there is no very solid recipe. We had some a paper by Huang Bo on the Bob survey, and he's a student of Jose Miguel. In their paper, they mask a region that is like 300 AU from the young cell objects. And they just within that radius, you should be cautious. Even within that radius, the polarization pattern is complicated, but can or cannot, may or may not be affected by scattering. But in their diagnostics, I think they removed that part. I suggested one thing, but they didn't use it, is to study give estimate on the optical depth in that. If it is optically thin, then you are safe to ignore the scattering. Scattering, you must go to top of like close to 1 or larger to have an effect. And also, do you expect grain growth? If you don't think the grains are 100 micron or larger, then it's fine. If it's 10 micron or smaller, scattering is not very efficient.
So you said that we can distinguish the cell scattering beyond the optical depth. So you said that if the optical depth is below 1, so we can ignore the cell scattering from the dust polarizations. But as you showed previously, if grains is not compact, but it has porosities, like had a high porosity, so even the polarization spectrum is very wide like this. So maybe even the optically thin cell scattering can have some effect here. So how we can distinguish this case?
No, so that curve is plotting the polarization scattering opacity as a function of wavelength. If you include porosity, it actually makes things even worse. So the response window as function of wavelength is wider. However, the peak of polarization is also reduced. So you cannot be too fluffy. even for the same model, if you are too fluffy, then too porous, for example, filling factor smaller than 0.1, you may not even be able to produce scatter-induced polarization at all, even in the opposite case. So porosity only makes things worse in terms of producing high polarization fraction.
Yeah, I think regarding the first question, I would like to add a little bit. So first of all, there are two key signatures to distinguish the polarization mechanisms. So first of all, the polarization degree. So for the polarization by self-scattering, the polarization level would be less than a couple percent. But the polarization by magnetic alignment or mechanical alignment, it would be as high as 20%. Okay, so because self-scattering, that means photons must be scattered several times. So the polarization basically is diluted. But in the case of magnetic alignment, the polarized emission is very highly polarized. So that is the first signature. So the second signature is the wavelength dependent polarization angles, right? So self-scattering is very sensitive to the wavelength, assuming that the maximum size is the same. So if we see the polarization angles varying at several wavelengths, then that is a signature of, no, if the polarization angles are the same across several wavelengths, that means the polarization mechanism is produced by alignment. So alignments, alike grains can emit the same polarization at several wavelengths. But self-scattering, it would make at some wavelengths, self-scattering polarization is dominant, but at other wavelengths, polarization by self-scattering is subdominant, and then the alignment becomes dominant. So that results in the change in the polarization angles at different wavelengths. That's what we observe from HL tau.
Yeah, but in observations, a lot of cases, we only have one band. Like the Bob survey, they only have polarization observation at one band.
One band, yeah, but other people will propose for other bands.
yeah. But it's hard to get the same resolution.
Oh yeah,
as band slider.
So we have to combine polarization degree, polarization angles, as well as other observational tracer like the thermal dust emission, because it can help us to constrain the maximum grain size. So, nature is quite complicated, but somehow we can only now tell that, okay, there are two dominant mechanisms that produce polarization. That is already good enough.
So may I ask one question? So, Ginny, you have still second question.
So second question is in disc regions, it is hard to apply the DCF method and it has a toroidal structure. So I wonder which method I have to use to estimate magnetic field strengths in the disc region.
Yeah, I think that is very important. The whole community is looking for the technique to measure magnetic fields in the disc. So because dust polarization has been ubiquitous, so that's why people try to use dust polarization to measure magnetic fields, but it's quite unsuccessful. But there's a missing technique is based on the molecular light polarization. So it's named Gold-Dry killer fish effect. So basically,
I don't see any observation.
No,
I know in jet, but not in disc. It's hard to achieve.
Yeah, only a few papers exploring that.
Not in disc. So Ian Stevens is doing this a lot, but we don't see it too much.
Because we saw some paper by the Fleming et al. And his group. So I think they published a couple of papers about that.
Online polarization.
Yeah, the molecular light polarization.
We're also working on Zeeman. There are so far 3-4 disks with Zeeman observations, but we only have upper limits. Somehow the upper limit is just about right. So it's on the same order as what we expect. Magnetic field should be like milligauss. All the upper limits are all of milligauss. But it's quite expensive.
But I think in GMAT, the disk structures, it could be affected the rotation of the molecular lines. So it should be remove the rotational effect and then calculate the GMAT.
So in that way, in the data processing, we do take into account the capillary rotation. So we stack at each different points of the disk, taking into account the radial velocity expected from capillary rotation and stack data together. But after all of this stacking, the signal noise is not enhanced enough to claim a detection. So we only have uplink.
Okay.
Okay, so I asked maybe Sang and other. So in the it's not still not unclear now, still very unclear to me that the size distribution, the function for the size of grand distribution in disk we use. I assume it's not MRN distribution things, right? So what kind of distribution are you using in your scattering model and your grand alignment model in the disk? And also the second concerns of, no, sorry, the second question is about a very important thing about the new anisotropic grain growth, because that will that will completely different from the isotropic grain growth before, right? We know that. In the past, when we have grain growth, the grain will be more likely roundish shape, but now, yeah, so the elongation aspect ratio increasing as we grain size increasing, so that something can be very important to take into account in future the workflow.
Yeah, so I think in the literatures there are usually 3 ways to treat distribution of dust grains. mRNA is the most used one, or a modified power law, not only just 3.5, but some sort of power law. The second is some people use log normal. The other is like Gaussian, centered at 1 wavelength. But for the scattering, it doesn't really matter too much because it's only one size of grain that matters. You can use whatever you want, and at the end, the result will be similar, but it may be normalized between different models by what is exactly the grain size, but the grain size that is operating always has a size factor of 1. Yeah, it's a very sharp function as opposed to the absorption opacity.
It's a scattering, the size is more important than the...
Yeah. So for example, in the small grain size limit, the scattering opacity goes as a to the cube. So it's very, very steep. Only as of but when you go beyond the x of 1, the Mie theory kicks in, and there's a lot of oscillations because different parts of dust grains will have different phases. A lot of cancellations comes in, and the polarization fraction is reduced very dramatically. So whenever you use Mie theory, you always have very, very sharp response window. And because of that, the exact choice of your dust model doesn't really matter too much. Yeah.
Yeah, okay, so I would like to mention that the MIN size distribution is just an empirical size distribution. It's not the size distribution derived from first principle. So we should use that as a reference only. So we should choose different size distribution. Okay, now the second question by Chum is about the change in the grain elongation. You know, the whole community, when people work on grain growth, they only care about how the size of grains increase during the grain growth. And then that is quite, it has a very important implication for community who work on polarization. Because when people explain the depolarization towards denser region, many papers in literature still explain that the decrease in the polarization is because when grain grows, grains become more spherical. and because people don't know how grain grows change the grain shape. But it's certainly in contradiction to what JCMT and ALMA observation towards denser region where grain grows is significant. We still see very strong polarization. That means grains are not spherical. And then we have to understand why. And then we propose a new mechanism that can make grains grow and not only in size but in shape, in elongation. So we try to unify the two communities, the community who work on grain growth and the community who work on magnetic field and dust pollution. That is our ambition.
That's quite ambitious.
Actually, I also have a comment on that because, for example, Bảo and I also do study the G11 filament, and we find that if we have to change the elongation from the outer to the inner region, if we not, if we didn't change the polarization function of our numerical model cannot reproduce the observational data. So we also think that we have to change both AMAC and elongation from the
By elongation, I mean the aspect ratio. The ratio between the two axes.
Oh yeah, that is the ASO ratio. Yeah. So which means that we cannot explain about the multi-wavelength.
How much you are changing from which?
Actually, for the outer region, the ratio maybe 1 point something, but 1.4 or 1.6. But the inner region, we have to change it about 2. Yeah.
Agrees with us.
Yeah.
Keep it simple. Maybe.
Yeah, install Scrum, yeah, for sure. And I think that's really like the way that, yeah, Jack with her calculation for the aspect, the relation between AMAX, maximum grain size and aspect ratio. She show more or less the same because we use starline outside the core. It's around, it's interstellar medium kind. But inner to the core, we need to have the maximum quite high, about micron size you said, and also the aspect ratio about 2 or 2 point something.
Okay.
And I would like to know the time scale of that can happen, because we know that the pre-stellar core, the time scale is about, I don't know, million years maximum. If we have star formation activity in the middle, so the construction should be around 1 million year maximum. And if the time scale is shorter than that, it's very likely. Otherwise, it cannot. So I think team proposed a new mechanism, but I think more work need to be done, right, in order to have like quantitatively quantify something. Yeah, that's really waiting for.
Maybe I have a question for Shiwei. How about Hall effect? Is it not a factor anymore?
Well, in simulation, yes, it does have some effect, but observationally, it's hard to test. So we try some simulation result to see how the whole effect looks like observationally. And it turns out it's really hard to detect because the integration around outside the whole effect feature only appear right outside the disk and along the midplane. Not along the midplane, but basically along a certain scale height. So it's hard to detect that. And also whole effect also be efficient only given radial or density range. So overall probably is not as prominent as ambipole diffusion, which can working like along a wider spatial range. Yeah.
So in the disk scale,
Yeah.
I think the Hall effect is discussed much more than the disk formation community.
Right. I think density, if it will be different inside is where density is higher, right?
Right.
Yeah.
So one signature of Hall effect is that it strongly depends on the direction between the omega and the B.
Yes.
And it's if you change the B to opposite direction,
Yeah.
all the other effect remains the same, but Hall effect will change your
Right. That's only
So
a key feature. Yeah.
You may naively think that there is a bimodality in the disk formation.
Yeah, but observationally we don't see that. Yeah.
Okay. Well, what's the reason for it? So it's just Hall effect not important.
Right. I guess the observed size distribution is different from the bimodal predicted by Hall effect. Yeah.
Okay. Okay.
Yeah, okay. So thank you very much for everybody for the very efficient session. So it's time for lunch break now. The lunch is downstairs and we will come back at, let me see, at 2 p.m.
2 p.m.
Yeah.
Long,
Okay,
long break.
thank you.
Quan tâm